So this is a continuation of the background, an overview of the background notes on functions. Let's continue on. The vertical line test is something we use to determine whether a graph is the graph of a function. Any vertical line can intersect the graph of a function at most one time. So here's an example of a function, y equals 1 over x plus 2. That was on an earlier page. Here's what its graph actually looks like. And see, any vertical line that we imagine in this picture is going to cross the graph at most one time. So that is a function. But if a vertical line can cross a graph twice, like the graph of this circle, for example, the graph is not the graph of a function, because what we see is we see two output values that correspond to the same input. And often in graphing, not always, but very often, the output values are y coordinates and the input values are x coordinates. So we got two y's that correspond to the same x. That's what the vertical line test points out, and so we know if in this situation we do not have the graph of a function. There's a special kind of function called a one-to-one function if no two elements of the domain correspond to the same element of the range. One-to-one functions are the simplest kind of functions. This example number 1 on our handout is a one-to-one function. And with a one-to-one function, all the arrows start at just one domain value and end up at just one range value, so it's very straightforward. This third example, postal zip code, which is a function, but that example is not one-to-one. So while each input has just one arrow starting at it, you can have multiple arrows ending up at the same output value, and that would not happen with a one-to-one function. It's easy to recognize a one-to-one function from a graph. Now here are two graphs. The first, y equals x squared, that is a function, but it's not one-to-one. There's actually something called the horizontal line test for one-to-one functions. So the vertical line test is satisfied by both of these. But the horizontal line test, if we apply it, we can find a horizontal line that crosses this graph twice. That means there are two different x values that correspond to the same y. Two different x values that have the same output. With a one-to-one function, horizontal lines will cross the graph at most at one point. So y equals x cubed is an example of a one-to-one function. Now let's talk just a little bit about function notation. You should have some familiarity with function notation. And we're going to go through these exercises. But just before we plunge into the exercises, realize that when we write this f of x notation, so the way you read that is you say f of x refers to the y value that corresponds to x. It does not mean f times x. It has nothing to do with multiplication. And let's look at a few examples of function notation here. I'm going to recopy these onto the paper. So I'm giving you two functions to work with. One is f of x equals x squared plus 5, and the other is g of x equals x plus 1 over x minus 1. These are both functions, and we want to evaluate f of 3 in this exercise. Well, one way to think of function notation is it just says take whatever inside parentheses and plug it in for x, right? So we get 3 squared plus 5, which is 9 plus 5, or 14. Okay. G of 2, just plug in 2 for x in the g function, 2 plus 1 over 2 minus 1. 2 plus 1 is 3 over 1 is 3. We can think of the letter f or the letter g too as sort of like the name of the function, right? Like this function is the f, has name f. This function over here is name g. Now let's compute these next quantities. F of x plus 3 in parentheses. And now before I do this, I just want to say something about the way I think of function notation. I kind of wish we wrote function notation without an x, but I wish we just put an empty box in the parentheses. So instead of writing f of x equals x squared, I wish we wrote f of box equals box squared plus 5. Because there's no reason we need to use an x. The function here just means take whatever you have, square it, and add 5. So if you have something more complicated inside parentheses, like an x plus 3, function notation tells us to put if the x plus 3 is here, it also has to go in this box, which means f of x plus 3 is x plus 3 in parentheses squared plus 5, which would be x plus 3 times x plus 3 plus 5, or x squared plus 3x plus 3x, that's plus 6x plus 9 plus 5, or x squared plus 6x plus 14. So there's f of x plus 3. And let's look at g of z plus 2. I think they want us to figure out g of z plus 2. Now, the g function, if I wrote it in this box kind of way, because x occurs twice on the right, I would have to write box plus 1 over box minus 1. Whatever is in the box here for the g function gets put in both those spaces to the right. So if it's z plus 2, I need a z plus 2 here and a z plus 2 here. So the g of z plus 2 is z plus 2 plus 1, and g of z plus 2 minus 1. The parentheses don't affect the values of the calculation here, right? That's could be written without parentheses. So then I can combine like terms. I get z plus 3 over z plus 1. There's the simplified form of g of z plus 2. So let's just make those stand out a little bit. Now let's just compare a couple more. F of x plus 3. And I think g of z plus 2. And I just want to make sure everybody realizes these are different. This is saying that just take the f of x function expression, x squared plus 5, and just add a 3 on the outside, which will be x squared plus 8. And I guess the point of this is to notice that f of x plus 3 in parentheses, and this f of x with the plus 3 outside the parentheses is very different. For the function g of z plus 2, we just take the function original expression for g of z, which, so I would just change the x to a z, z plus 1 over z minus 1, and add 2 to it. And you don't have to do anything with it, but if you wanted to combine, I'm just going to write out the algebra quickly here. We would take 2 over 1, we'd have to multiply by z minus 1 over z minus 1. And we get a common denominator here. Z plus 1 plus 2 times z minus 1 over that common denominator of z minus 1. And I guess I'm going to squeeze that in here on the side so I don't, so let's see, I got to distribute the 2. So I have z plus 1 plus 2z minus 2 over z minus 1. That becomes 3z minus 1 over z minus 1. And the main point is just to realize g of z plus 2 in parentheses, this g of z plus 2. They're very, very different. Okay? So there's just a little bit, I mean, that's not teaching us all about function notation. This is just meant to remind us of the basics. And I think we have just couple more thoughts here, and we'll finish up this review. Even functions and odd functions we're going to talk about. A function is even if, really this is the defining property right here. I should have put a box around that. If you can always say f of minus x equals f of x. A function is odd if f of minus x is equal to minus f of x. And I think I've already slipped these words into the discussion a little bit. The name even function comes from even powers of x, because this property is held by even powers of x. And it's kind of like saying if you plug in a positive or its opposite, the y value, the corresponding output value or y value is the same. So like with x squared, if you plug in 3 or negative 3, you get the same y. They come out the same. With x to the 4th, if you plug in positive 5, negative 5, they come out the same. And that is same is true for cosine, because we've looked at how cosine of minus theta equals cosine theta. The graph of an even function is always symmetric around the y-axis. The two halves, if you fold along the y-axis, will come together. An odd function has a slightly different property. It's saying f, when you look at opposite x values, it's basically saying their y values are opposites. So f of the opposite of x equals the opposite of f of x. And that's true for odd powers of x, and that's where the name odd function comes from. If you plug in 3 or negative 3 into the x cubed function, one comes out to be positive 27, one comes out to be negative 27. They're opposites of each other. And that's also true for the sine function. Odd functions have a certain symmetry. You can't just fold this in half, but this is called symmetry around the origin. And one way to imagine what symmetry around the origin means is if I turn this picture upside down, an odd function looks exactly the same. So that's it. And we're going to start going back to trigonometry in the next segment.